Okay, AP Chemistry kids, this is part 2 of the first kinetics lecture where we're going to talk about the method of initial rates. We talked about that rates can be either differential or they can be integrated rates. This method of solving for differential rates would be under that differential category. The instantaneous rate, initial rate is defined as the instantaneous rate just after the reaction begins. And what we do is we determine several initial rates using several experiments with altering, as you can see here, the concentrations. Okay, so let's take a look at what an example problem could look like. Here you have methanol decomposing into methane and into CO, carbon monoxide. You'll notice that we have a couple of trials here. We have trial 1, in which we have a concentration of 0.1, and we also have a rate with various rates with various concentrations. Okay, so when we're doing the method of initial rates, we're going to take this data and we are going to compare it with another as a ratio to determine that rate law. So you'll see here that it says determine the order and also the K for this reaction. So that's what we're going to do here today. So let's see, we're going to go with black. I'm going to make this pen a little bit thinner, and here is the problem here that we are working with. So what I like to do is I like to compare two trials. And so I would compare, let's get this going here. Yep, it should be going. I don't know why my pen isn't. I'd like to compare the rate, okay? And when I compare the rate of 2 over the rate of 1, this is really not working well. Let's see. Okay, so we jump back to this slide and we're going to look at a initial rate problem in which we are comparing, we're going to compare trial 2 over trial 1. And we're going to take, what we're going to do is we're going to take this data. So we're going to take the data from these two trials and we're going to put them in a ratio to determine the order and to determine the value of little k. So what I did on the next slide here is I went and I'm making my ratio where rate 2 over rate 1, which would equal the rate law. Rate 2 would have a value of some specific rate law times the concentration to the nth power that you see here. And that will be over what you can see here, rate 1 times the specific rate law to the concentration, this representing the first trial to the nth power. So what I did is I took this data from up here and I am plugging that in, and I would have 0.34 over 0.085 equaling 0.2 over 0.1 to the, this should actually be to the nth power. So that's a big N that you see there. So then when we solve for N, this ends up becoming 4, this becomes 2, and this would be to the nth power. In this case, N is equal to 2. So what we say, and we actually would say it this way, is that the reaction is second order. So now, once we found N, we know that N is second order. We would write this rate law then like rate equaling some specific rate constant times the concentration of CH3OH, because this was the reactant we were looking at, that concentration to the second order. That's a 2. Now, what happens then is if we look at a new, take a new sheet here, and what I notice that is that once N is found for, you can solve for K. So you solve for little k by taking one of the data points up here. So let's just say we're going to look at trial number 1. We're going to take that data from trial number 1 and we are going to plug that in to solve for k. So I can say that rate is equal to the concentration of CH3OH to the nth power. Oh, and there's that little k should be right in there too. So now I'm going to plug in. I do know what the rate is. It's 0.085 molarity over a second. And I do know that this is equal to K times the concentration, which is 0.1 m. That's capital M, and it's second order. Okay? So now when I solve for K, K is going to equal 8.5. And we have to consider, what is the unit? Well, the unit would be, as you notice here, we've got m over s, which is molarities over seconds. And then here, because of the squared term here, I would be squaring molarity. So when I am simplifying this, I'm actually going to write this. This would be m over s over meter squared. Now what's going to happen is that meters is going to cancel out. Oops. Or I'm sorry, that molar is going to cancel out. Still having troubles. This molar is going to cancel out. Here we go. This molarity is going to cancel out. And what I end up with is 8.5, which would be m to the negative 1, s to the negative 1. And that is what's equal to my k. When I said there that it was meters, I meant molarity. Capital M in this example means molarity. So we would rewrite the rate and say rate is equal to 8.5 m to the negative 1, s to the negative 1, then times the concentration of A, in this case squared, and in this case A was the methanol. Okay, so now the next problem will become, what happens when you have two reactants? How do you find the order for the reaction for more than one reactant? Now remember, you're the scientist, so you get to design the experiment. And what I like to look at when I'm going here is that I like to look at these concentrations. Do you notice for NH4, they're exactly the same? And then notice how that rate is changing, because this is doubling. Here, I'm going to go in a different color here. Do you notice how this is doubling? Okay. Is that rate doubling? So you might get well and do well that you can actually just even see the order just from looking at the data. And especially with the AP test in the spring, I recommend that you do that. However, you still have to show your work somehow, whether that be incorporated in the table, like you say, this is doubling and so is the rate doubling, so therefore it's first order. But you do have to somehow show your thoughts as far as what is happening there. But what I'm going to do now is that I am going to talk about how we can use the fact that the ammonia ion is constant with the NO2 ion changing, how that can look, how we can make that work for us to calculate the order. Okay, so what I did here is that I'm going to take the data again and compare trial 1 and 2, and you'll notice that since the concentration of the NH4 is constant, that is going to make this all cancel out, as well as the rate constant will be the same number, so that's going to cancel out into a big fat 1, and we can compare the rate values that are in the data table, which are right here, to the change in NO2. So I'm going to write that out here. Okay, so then substituting, as you can see, substituting the data for what we had up here. So this data and this column right here. Actually, not that column. Let me get rid of this. So actually substituting in what's highlighted there You'll notice that we have taken then the 2.7 divided by the 1.35, and then again from the data here, we get a 2 is equal to 2 to the n, where n is equal to 1. So then we have this verbiage that we say about rate orders, and we'd say that this is first order with respect to NO2. Now, what's going to happen is you're going to do the same thing for the NH4 ion. Let's go back up here when we go to the NH4 ion, and let me erase what I've highlighted here so we can take a look. Do you notice that the concentration of NO2 is staying constant in trials 2 and 3? So this is what we're going to compare here next. Okay, so plugging in then the data from trial 3 and comparing that to trial 2, we would get 5.4 times 10 to the negative 7, which would be the rate, over 2.7 times 10 to the negative 2nd for trial 2. That is all going to equal 0.20 to the nth power over 0.10 to the nth power. When we simplify that, we get 2 equals 2 to the m, and m equals 1. So again, we would say this is first order with respect to the ammonia ion. Now there's something also called the overall order, and you can get the overall order by adding up all the orders that are in the rate law expression. So if I'm writing this rate law expression, rate is equal to, I've got calligraphy pen there, rate law is equal to K times the concentration of N of the ammonia ion to the first order times the concentration of the NO2 to minus ion to the first order. We would say the overall order is 2, where we take the orders that you had solved for, right here, 1 plus 1 equals 2. So the overall order is 2, okay? And then we can solve for K by plugging in one set of data, just like you did in the previous example. That is how we calculate with the method of initial rates in differential rate law.